All right, here we go. So there's a couple of things I want to point out to you guys. We're the whole point of all this physics stuff is we're going to build a roller coaster. I do want to highlight that this is a frictionless roller coaster that we're talking about. Okay? Frictionless means that we're going to ignore friction. There is no such thing as a frictionless roller coaster. This is a nice way to say we're not going to bother you guys with trying to calculate the friction right now, but we want you to get the concept of conservation of energy. So remember, when it comes to the conservation of energy, that your initial energy will always equal your final energy, the total combined energies. Okay? And also remember that your mechanical energy is equal to the kinetic energy plus the potential energy. All right? And so here we have a roller coaster. And the question is, will the cart make it over the hill? And what I like what they did in this little example here is, notice that, well, that isn't highlighting very well. Oh, because I clicked the eraser. Notice that this is gray, and that's, it's gray up to the height of the hill. And what are they trying to say by that? Well, yeah, the cart will make it that high because the cart starts off much higher. So it has the potential energy. If it's frictionless and we're not using up any of this energy, it'll definitely make it over the second hill. Does that make sense? Now, if the second hill was higher than this point here, then it wouldn't. It would only go up that high if it was frictionless. Okay? Can I move on to the next? You have a question? If it was frictionless, yes. It would. I don't know if it'd go over. It might stop right at the top. I mean, if it was the exact same and it was frictionless, But yeah. So the reason for that is when the cart is sitting still, technically it only has potential energy. And whatever level of potential, like if you assign a number to it, let's say it's 500 joules, 5,000 joules, whatever that number is, that's how much energy you have in the cart. Now, as it rolls down to the bottom of the hill, it gets converted to kinetic energy. That kinetic energy is associated with 1/2 times the mass. We'll do the problem in a second. But it gets converted to kinetic energy. And as it climbs back up the next hill, it slowly converts that kinetic energy back into potential energy. Because even if you have, let me give you an example. Even if you have one that's like, well, actually, I'll just show you right here in class. This is kind of a neat thing. We've been working on this. My ICT kit tab, we're going to use this for us too. But look at this part, right? Now, this uses up a little bit of friction, okay? This uses up, I got to get this thing in here. Okay, this uses up a little bit of friction. Notice that it's able to go through the loop and go up to this point here, okay? And I think I showed you guys this the other day. Look at the maximum height here. See how high that is? Now we use up a little bit of, I got to put it on the cart right, or put it on the track right. I don't like how he rigged it. He rigged it to go from the other side, and I don't have time to do this because I'm recording a video. But basically, let me draw it out so you can see it a little better. If you have that second hill higher, it'll just go back down the hill. In other words, if I have this hill here, and you go down, and then the second hill is higher, and that's not the best hill. Let me make it look more like a roller coaster. So if you come down like this, and then it goes up higher like this, the path that the cart will take is it's just gonna, if the cart is here, it'll go down the hill and it'll go to the same height, whatever this height is, and then it'll stop because it runs out of kinetic energy, but it still has potential energy. Gravity is still pulling it down, right? So what will it do? It'll come right back up if it's frictionless. Only if it's frictionless. Does that answer your question? Okay. Let's move on to the next slide, can we? All right, cool. So when this thing is released from an initial height HI, or H sub I, or height initial, or H initial, what is the speed of the cart at any other point on the track? Well, we can calculate that. We can calculate that by closing the system. So let's go to the next slide. You don't have to write anything down. Well, I guess if you want to, I'll wait. Go ahead and write down the question. I'm wearing my Wonder sweatshirt today. Has anybody ever been to the Wonder Museum in Chicago? You should go. It's kind of fun. Not that expensive either. Parking is pretty decent. It's a pretty neat place. Yes. I don't know. It's kind of like an artsy technology thing. It's not an art museum, but they're creative people that use lights and sounds and cameras to do kind of artsy things. Yeah, there's a room that's nothing but mirrors, and then they have these cool glass things in there, and then there's a room that the lights turn on as you walk through it. They have this one thing that's hooked up to like almost like a drum machine, sample machine, like with pads. And when you hit the pad, it'll make sounds, but it also shows lights, so you can make like your own song. And as you're making your song, there's different images that light up. It's pretty cool. I liked it. Anyways, that's the hoodie I'm wearing. I just saw it in the camera. All right, let's go. Does everybody have this? All right. So I do want you to write this down. This is a big one. I don't know if you need to write all of the words. Maybe you should, if you don't remember what these things stand for. But basically, the initial energy is going to equal the final energy. That's the conservation of energy. This is how we figure out what the velocity of the cart is at any point in time. If we know that initial height of that initial hill, that tells us the total energy in that car. We calculate that. There's a formula for that. That energy, because the energy is conserved, and if we assume that it's frictionless, in other words, we're going to completely ignore the friction. Well, let's assume that it is frictionless. Then when we do all this math, everything is conserved. Not one drop of energy gets used up for friction. Okay? So if you're asked for the speed, you can just use this equation for the energy conservation to find the unknown kinetic energy. From the final kinetic energy, you can determine the speed or velocity. And we'll do this together as a group in a second. Can I keep going? Are you done? Okay. So let's do it. Don't write any of this stuff down. What we want to do, I just want you to look at the screen because after the slide, we're gonna write some stuff down. How do I figure out the velocity of this thing? Well, first of all, if you notice, I'm gonna have to close off the system. So what I'm gonna do is I'm gonna close off the system. Right. So remember, last time we met, we talked about open system and closed systems, and I kept saying, well, we can close any part that we want. Well, I'm going to close off this part of the system because that's what's going to help me. Where part one, all this part one stuff this is the initial stuff. So all this stuff here, the part one, that's my initial stuff. And then part two over here, that's the final stuff. Okay? And you don't have to write this down yet because I'm going to write it down in the next slide. Okay? All right, let's do it. They give us some information. How do I solve that? Woo! Okay, here we go. So remember, and this you got to write down. This is important. You should start writing this down. So remember, this is my initial energy over here on the left-hand side of the equal sign. And then on the right-hand side is the final energy. So this is, in other words, the total energy is conserved somehow, some way. Okay? Well, they give us some information, but they want to know what is the final velocity, right? So we're going to have to do some stuff. And I think we did one example of these the other day before the bell rang. Look at that from an algebra perspective. What do you notice about each term? Look at the variables. Is there something I can factor out of every term? What can I factor out? That's not meters. What does that M stand for? Mass. So I'm going to factor out the mass. In other words, if I divide this by M, and I divide this by M, and I divide this by M, and I divide this by M. So you could technically do this problem, and you don't need to know the mass of the car. Isn't that funny? You don't really need to know the mass of the car in this particular case. So if I give you a homework problem and you're like, and the formula says 1/2 times the mass and blah, 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 and you're like, Mr. Adams, you didn't give me the mass. You don't need it. Because the mass of the car is the mass of the car throughout. The mass doesn't change. So it's all proportional. So when you cancel it out. So now what does that give me in my next line? Well, in my next line, and I'm going to write this over to the side because we got to do a lot of math. That gives me that my initial height, my potential energy, and you guys, let me write that over here. Remember that your potential, your potential energy is always going to be 1/2 times G times H, and then to find kinetic energy, sorry that I wrote that a little wonky, is 1/2 times the mass times the velocity squared. So that's where that's coming from, the initial potential energy plus the initial kinetic energy. So 1/2 times VI squared has to equal GHF sub F plus 1/2 V final squared. Okay. Now, I'm not quite sure how you guys want to do this. You could do this algebraically and solve for VFs, or just plug the numbers in. I'm just going to plug the numbers in just this one time. I tend to do the literal equations a lot. Anyways, this will be 9.8 times the initial height. That would be 30 meters. Plus 1/2 times the initial velocity squared. What's the initial velocity though? 0. So what's that going to end up equaling? I already screwed up. That would equal 0, right? So now, then I have 9.8. That's the acceleration due to gravity. Let me write that down so you guys remember. Remember that? G is equal to 9.8 meters per second squared. Times the final height, which is 16 meters. Plus 1/2 times the final velocity squared. We don't know what that is. That's what we're solving for, right? Okay. So, interestingly enough, this whole thing goes to 0, right? 0 squared is 0. 0 times 1/2 is 0. Because I'm having some software issues, I'm just going to manually enter this in the calculator. So 9.8 times 30 is 294. So this little thing right here, this times this is 294 is equal to, then I have to multiply 9.8 times 16, which is 156.8 plus 1/2 times V final squared, right? So then I'm going to subtract 156 from both sides. These will cancel over here. So let me do that, minus. And I'm gonna move this over to the other side here. That gives me 137. I hope somebody out there with a calculator is double checking, because Mr. Adams can make a mistake sometimes. Equals 1/2 times the final velocity squared. Remember, our goal is to get V sub f by itself. So I'm going to multiply this side by 2, and I'm going to multiply this side by 2, because 2 times 1/2 is just 1. Or you can think of it as I'm dividing by 2, so I'm going to multiply by 2. So over here I get V final squared, and I just got to multiply this by 2. 137.4 times 2 is 274.4, right? And then to get the final velocity, I just take the square root of this side. Whatever I do on one side, I have to do to the other. So let me take the square root of that. $274.4. And I get about 16.57, roughly. Okay. Yes. Yeah, it's meters per second. Sorry, I'm really yeah, that's meters per second. Thank you for reminding me. You know what's funny is I think in the video my face is all over the place. Let me see if I can move my face. Oh, there you go. I removed my face for a second. Okay, does anybody have any questions on that? All right, because it's